at the HOMO, for example, then you always have to say what method you computed at. I mean, a HOMO is not even a physically meaningful concept. So that's kind of the thing that always strikes me, how much effort is up there, and then how we end up being sloppy down here when we actually discuss our computations. So what I want to talk about today is two questions. The first, can we assign excited state character in a completely automated way? So you don't want to sit there, open Molden, click an orbital, wait for half a minute until it shows up, click the next orbital, and so on. So can we get rid of just clicking all those orbitals all the time? And then we can do larger data sets, but we can also remove personal bias. I mean, how do we know if two people look at the same orbital? How do we know that they come to the same result? And then, for example, maybe we want to analyze structure property relationships, just to give you a bit of a buzzword here, where we really get kind of quantitative insight. And then the other idea is kind of that we want to learn about physics beyond the MO picture. And here, especially, I'm thinking about exciton theory and valence bond theory. So those are actually two different ways of talking about electronic structure. And the question is, where do we meet, and how do we kind of, if we do computations within MOs, how can we learn about, exciton and valence bond pictures? So the outline is I kind of want to introduce you to the whole idea in terms of DNA. How can we assign state character? Then just kind of detour a little bit, go from DNA to push-pull systems and to transition metal complexes. Then kind of in terms of conjugated polymers, I just want to kind of be a bit more visual, show you how we can understand electron correlation with different plots. And then I'll go to the conclusions. All right, so the first question is, we'll look at DNA, we compute the photophysics of interacting nucleobases. This is something, I started out with this, working for Hans Lischka during I guess about 10 years ago. Oh, sorry, no, I just messed this up. So people care about what happens after DNA is excited by UV lights. You might transfer energy from one base to the next base. I hope you can see this again on the screen. Yeah, looks all right. Or electron transfer, exiplex formations in the dynamic processes. And we start out, we care about what the starting point is the UV absorption. So basically kind of in terms of energy transfer between different nucleobases, we just think about it as localized or delocalized states. And in terms of electron transfer, we think about charge transfer states. So that's what we start out with here. And then, yeah, we looked at polyadenine, kind of a single-stranded computations here. You see the system here. 8 nucleobases are treated in the QM region. So we're using TDDFT with a modern density functional. Then even then, we need to use a special implementation. We use the GPU-based implementation in Chem, have an environmental model. So there we have all the 3 things I wanted to talk about in the first slide. So we do have a modern computational method, environmental embedding, and a high-level implementation. But then, of course, once you start getting these amazing computations, then suddenly you hit the wall, because we had 100 snapshots in our molecular dynamics. For each one of them, we computed 60 excited states to represent kind of those 8 nucleobases as well. But then the question is, how do we analyze 6,000 excited states? At the end of the day, we have 6,000 excited states that we have to look at, and where we want to know something about them. So what do we do? And then here, just kind of to put in kind of the undergraduate slide. So what's the textbook picture? The textbook picture is, in the ground state, all the orbitals until the highest occupied molecular orbital are doubly occupied. And then when we have excited states, we might excite from the HOMO to the LUMO, or we might excite from the HOMO -1 to the LUMO. And that's kind of the textbook. So we just have to know what the HOMO and the LUMO look like, and basically we understand the photochemistry. But is it really like that? And then, okay, then we try out our computation, for example. So this is the output from Chem. Here on the right, I'm showing you the canonical orbitals, the HOMO, the LUMO, then some higher virtual orbitals, some lower occupied orbitals. And now what you can see is what TerraChem actually tells you. No, there's one that is not just a HOMO-LUMO transition, but it's composed of 3 different transitions. Same the S2 state is not just a HOMO-LUMO transition, it's composed of 3 different transitions. So yeah, so we also have multiple configurations involved. We can't just kind of look at one orbital and know what's going on. So on the one hand, and kind of this, I guess 2 things to complain about. On the one hand, it's tedious work because we have to sit there in Molden, click the orbital, wait until it renders, and then we see the orbital. But it's also the problem is that we have ambiguities, because now if we have those 3 different orbitals, how can we kind of get a unique way of really assigning what this all means? So then kind of the one thing is that we can go for visualization as the first step, that we do a singular value decomposition of the transition density matrix. I didn't want to show too many equations here. But the point is then when we start with the first state we had here, the state that needed 3 configurations, once we do the singular value decomposition, we actually find out that, okay, the HOMO -2 stays the same. And then the acceptor orbital is just a linear combination of these 3 orbitals. So what do we find out is just then we just have one important configuration that gives us 90% of the transition, and that's kind of located from here to here, always on the 4th base. So at this point, okay, some ambiguities are resolved. At least we have clear pictures to look at, but we're still looking at 6,000 pictures, and we're still looking at blobs of color. And that's also the thing that I complained about in the first slide. Let's say, kind of, we want to also have a more rigorous way of looking at things. So how do we go from there? And at this point, it just helps to take a step back and think about how do we understand excited states in multichromophoric systems. So here, for example, this is my schematic DNA. We have our 4 chromophores, and we have the backbone here. And now we could have a locally excited state on one of the bases. We could have a charge transfer state going from one basis to the next. We could have a Frankel exciton, so we would have a excitation over several fragments. Or we could have a charge resonance state where, again, several fragments are involved, but the electron and the hole are always on different fragments. So we talk about, the hole is where the excitation comes from, or the occupied orbital, the electron is where it goes to, or the virtual orbital. And here the thing that I want to stress is that the connection between electron and hole is decisive. So it doesn't just matter kind of overall where are the holes and where are the electrons, but it's also the kind of, you have to think about it as kind of 2 particles moving around dynamically. So for example, here we'll have coupled local excitations, that's what we call Frankel exciton, or we could have charge resonance states where we have coupled CT states. Both kind of are delocalized, but then when you look at whatever physics, at transition moments or kind of energy dependence with respect to separations, those are completely different types of states, but you wouldn't see it if you just kind of look at the canonical orbitals. All right, so then kind of, we want a 2-dimensional analysis, and then we think about kind of what's the quantity we could look at, and here kind of what I'm promoting is the transition density matrix as a basis. So where the idea is that we have kind of the ground state on this side, we have the excited state on that side, and we connect them with annihilation and creation operators. And when you think it through, then you can say, okay, this bit here, it doesn't even say it, but let's say then you can think kind of the one that pertains to the excited state is the electron, the one that pertains to the ground state is the hole. So then kind of this matrix is just a matrix that tells us where are the hole and the electron. So if this is our matrix in a schematic way, then we have the hole here, this mu indexed here, and the electron here, the nu index here. And now kind of we'll just look kind of which ones are the largest elements of this matrix, and then we can decompose this. So for example, here in the diagonal are the local excitations on the individual molecules, and out here are the charge transfer excitations. So then we press the button, and we'll get this decomposition into the individual local excitations and charge transfer contributions. So now the idea is that here we reduced the calculation to numbers. So we're no longer looking at blobs of colors, but we have a small matrix of numbers. And once we have that, we can start doing different graphical representations and statistics. And here, for example, what we did for that specific paper is then that we compute the delocalization length. So what people are interested in is how many bases are involved. So do we have a delocalized exciton or do we have a local excitation? And what we're computing here is the delocalization length. I mean, here messed up the slide, sorry. But so anyway, here kind of this omega belongs to that side if you wonder about this. But anyway, the point is now kind of if you look at this formula without this extra omega, which is just a normalization factor, then you can see if just one molecule is involved, let's say if just one of these elements is not 0, then we're going to have 1 for the delocalization length, and then let's say if you have 2 or 3 bases involved, then this delocalization length is 2 or 3. So then we have a continuous measure that tells us how many bases are involved in the excited states, and that's something that kind of people have debated about for a long time. So now what we do is we take our sample of 6,000 excited states that I talked about before, and we just divide into these different contributions. So for each excited state, we compute the delocalization measure, and then we divide into different bins. So is it about 1? Is it about 2? Is it about 3? And then we plot the absorption spectra for those individual contributions. So the total spectrum is shown here in black. So I hope you can see my laser pointer. Goes here. And then, for example, the next important contribution is in red. That's delocalization over 2 bases. And then comes 1 and 3. And the highly delocalized ones come down here. And it's just something that a question that kind of was hotly debated for a while. How many bases are involved? And I mean, of course, I'm not saying that this is the final answer, but at least that way we have a well-defined measure to talk about. So what we say, mostly 2 neighboring bases interact when a photon of light is absorbed. So they're not completely isolated, but we also don't have like something like band structure, things that are delocalized over the whole system. And then we can do a bit more statistics. For example, we can look at the charge transfer character, whether these are local excitations on one base or delocalized states. And then kind of when we play this game, then we find out that kind of 50% of the spectral intensity has less than 10% charge transfer character. So these ones are the local states or the Frankel exciton states. They make up half. But then what that means on the other hand is that also half of the states have at least a little bit CT character. And we see, for example, kind of the red line between 10 and 20% CT character. So these ones are states where we have some orbital overlap. Those are not proper charge transfer states, but we do have some non-trivial orbital overlap. And for example, you would assume that a simple Frankel exciton model or something like a Coulomb model would not work because we have an orbital overlap term here. And then, for example, the ones with high charge transfer character show up at particularly high energies here. So this is also an interesting question because people have talked about whether actually the red tail of the spectrum would be dominated by charge transfer states. But at least at our level of theory, we can say no, the charge transfer states go to very high energies. So then I just kind of want to go through it a bit quicker. How can we apply the same philosophy to different types of systems? So I started out with DNA, where you have separate molecules, and this is comes from my time in Vienna with Hans Lischke, and then you can kind of do the same, play the same games also with different systems. So for example, this is one thing from some synthetic chemists from Vienna that came to me, and they told me, yeah, they synthesized these amazing molecules with, you have the triple bond and the 3 nitrogen atoms, and then you have the triazole kind of click chemistry. And so they created different isomers, different oxidation states of sulfur, and then the question is just kind of, okay, now you run these computations and you just want to present the results in a compact way. And here just kind of want to show you how can we characterize states in push-pull systems. So this comes from a Chem Phys paper from 2020, and so Sebastian Meyer is actually the first one who kind of developed this representation. He's also in the audience now. So what we're trying to do is we put our molecule here. So we have a triphenylamine donor, and then we have 2 acceptor groups. There's this triazole ring and this sulfoxide group. And here first we plot the excitation energy. So the first 9 states go up in excitation energy. And we use the oscillator strength via color coding. So the orange state is the brightest state, then the brown state is the next one, and then the blue state is the next one. So here, that's just the standard information that we would tabulate anyway, energies and oscillator strength. Then the next thing that we're trying to look at is the localization and charge transfer. And here again, kind of this charge transfer number analysis comes into play that I talked about in the last slide, or like in a DNA bit. For example, we might have an excitation that starts on triphenylamine and ends up on triphenylamine. This is shown in blue. For example, this is the blue bit. Then we might have an excitation that starts on triphenylamine and goes into triazole. This is shown in green. And then we have different other contributions. For example, also from here all the way down here, this is pink. Or just anything happening down here is orange. And so basically and down here we compare to the natural transition orbitals. And for example, we can see the first state starts on triphenylamine and then goes into this, has a big contribution on triphenylamine and goes a bit into the other acceptor group. So this is represented here. The first state is mostly blue, but it also has some green, which is refers to the triazole. Then, for example, see the next 3 states are purely triphenylamine based. You can also compare this with the pictures, and this is also, of course, what the spectroscopists know, that kind of GPA has its band down here. And then you can look at the other states. So, for example, anything happening on the left side of the molecule is only at higher energies. So,
hey Felix, can you hear me?
Yeah.
Yeah. Why the character is not exactly 1 in the case of the graph 2? For example, the S1 is the character is about 0.8%.
Yeah, so it doesn't add up to 1. I guess the missing bits are either double excitations. So or I'm not quite sure if there's some contributions that we didn't compute here, let's say from triazole to TPA. So they're both things missing. Let's say double excitations we couldn't analyze in principle, and then the other things that just didn't include all the contributions, just to otherwise I'd have too many bars. So aside from the fact that kind of we don't have a few white boxes, we can assign the states automatically, and we kind of have the assignment here that corresponds to the orbitals, and then for example, you can look at trends. You can see how things change once we change the substitution or whatever, the conformation of the molecule. All righty. So then just kind of, because I was asked to show some different examples, I also want to show you this complex. So this is a rhenium complex with a bipyridal ligand here, chlorine here, and CO groups here. This was introduced to us by the group of Chantal Daniel. And now, again, we compute the excited states and want to know which states are involved. Did do MS Caspity-2 calculations, so it's high-level computations. We compute 19 singlet states and 18 triplet states. So we do, these things are not easy to compute, but those methods exist. But now the question is, how do we characterize so many states, especially, let's say, if we want to do dynamics with it later on or something of that sort. So, okay, then just kind of to start out with, we look at the transition density matrix. Before I was just showing you this matrix, but we can always transform this into a two-body function if we just multiply this matrix with the appropriate atomic orbitals. So, and then kind of we get a two-body function that gives us the probability distribution of the hole and the electron. So kind of the square of this function is the mutual probability distribution of the hole and the electron. And for example, then we can compute the density of the electron in the hole. So this is basically the attachment-detachment density just by integrating this thing over one of the coordinates. And then again, then it's kind of the storyline, same storyline as before. So now at least we have a rigorous depiction of our state. We see the hole is on this side, the electron is on this side. So this is a clear metal to ligand charge transfer state with some involvement of chlorine. And I mean, if you ever worked with these transitional metal complexes, they can be a real pain because the canonical orbitals are just all over the place. And at the end of the day, you have no clue what's really going on. And yeah, we're still looking at blobs of colors to stick with that theme. So yeah, so then we use the same trick that I introduced with DNA. We compute the charge transfer number. So again, this is the transition density matrix. Similar thing as before, only here, for example, I'm using Loftin orthogonalization to make sure it's a rigorous population analysis. And I divide this into my central metal and the ligands. So, and then now when you think about it, then we can decompose the transition density matrix, and then we have a hole and an electron position. And the nice thing here is that actually this exactly corresponds to the way that people like to talk about excited states in these systems. So a metal-centered state is if the hole and the electron are both on the metal. A metal to ligand charge transfer is if the hole is on the metal and the electron is on the ligand. And then intraligand is if both are on one of the ligands, and so on. So it happens that kind of exactly this fragment-based view is the one thing how people talk about this state. So that's why we have an automatic classification of state character, and we can also quantify state mixing that would be difficult to quantify otherwise, for example. So, and then, yeah, so for this thing, I divide this into three fragments. You have the bipyridal here, you have the rhenium and carbonyl here, and the chlorine up here. And so this is the same plot that we had before. So I look at the singlet and triplet states. Those are shown here. I can show the energy here, and then this decomposition again. Again, some contributions are missing, either because they're double excitations or because it's just different directions that I didn't include. But the point is, we can start discussing things. I don't want to discuss, let's say, I don't want to talk too much about kind of the chemistry here, but the point is, for example, we see that the green bits are the chlorine states, and only the singlets have green bits. So for example, only because apparently we get low energy chlorine states only because of exchange repulsion. And then on the other hand, we see if we look at the blue ones, the local ones, the blue ones are mostly triplets. And that's, of course, let's say, kind of if we have the blue ones here, because a local excitation, a local singlet would have more exchange repulsion. That's why we tend to have low energy local triplet states. So don't want to talk about it too much, but the point is you have kind of this really an automatic but also a fine-grained way where you can start discussing subtle trends. So
what's the best way to select the fragments in a molecule, for example?
So I mean, let's say if you have a transition metal complex, then you can kind of do the transition metal and the ligands. If you have a push-pull system like we had here, then it's also kind of logical where the push part is and where the pull part is. If you have a complex, it's logical, but there's no, let's say there's no generally speaking perfect solution. So you have to kind of know about the chemistry beforehand before you select it. So yeah, so we have the fragment-based analysis. So at least if you have fragments, then you just press a button and you can assign the fragments. As I said, sometimes it's a bit ambiguous how to select fragments, and there's also a method by Sebastian Meyer that we did in a paper in Coordination Chemistry Reviews, how to get an automatic fragment selection. I'll also talk about kind of methods that give you information without needing any fragments at all. But of course, I mean, that's kind of the weak spot here that you need to think about well-defined fragments if you want to do any of these methods. Yeah. So see, I just predicted your question. The definition of the fragments is not always obvious. So we have to think about how can we move beyond that. And the way that I like to do it is, okay, then we go back to our two-body function. Sorry, the slides are not completely consistent, but here I call this an exciton wave function. But again, this is just a transition density matrix as a two-body function in space. So we have the coordinates of excitation hole and excited electron. And now that we have this effective wave function, we can go ahead and compute operator expectation value. So we just plug the operator in between here, and then we just normalize it to have a consistent result. And for example, what I'm doing here is kind of the average linear separation of the electron and the hole. If you think about it, this is just the dipole moment in essence, or the change of the dipole moment of your system. You also compute it exactly the same way as the dipole moment. So for this bit, we have some more complicated descriptors as well. But this means then we can define charge transfer without looking at any fragments. So we don't have kind of the question, how do we cut the thing apart? And we also don't have to worry about kind of do we do a Mulliken population analysis, Luftin population analysis, or should we go into some more fancy things like atoms and molecules? All of that falls away because we just compute this number. So the point is now, maybe just to show you that kind of, so if you look at the crosses first, so the crosses are the things that depend on the transition density matrix. And for example, you see the black crosses are always a bit above the red crosses, because triplet states always have a bit of a larger charge transfer character than singlets has larger charge transfer than triplets, because they want to avoid exchange repulsion. So even this kind of subtle trends you can see, then, or if you go back to not so subtle trends, for example, if you look at the very low values for the crosses correspond to blue bars, because low charge transfer corresponds to blue bar, and blue bar is the local excitation on BP. So we get the main assignment between charge transfer and no charge transfer, and we get also some more subtle trends And then if you want to dig deeper, then kind of there are two different ways. You can have like the transition density matrix, and you can look at the relaxed density matrix. And then you can see that when you kind of, this is related to kind of coupled perturbed cone-Charm equation. And you see kind of once you relax the density, then actually the charge transfer gets smaller. So the primary excitation separates the charges, but then the density relaxes to kind of compensate some of this charge separation. So that's kind of an effective charge screening that we can also see here, just with our little crosses and dots. All right, and then just kind of to give you a bit of a different type of thing, that a more recent paper from the Gonzalez group again. This is about kind of, we're looking at ruthenium complexes, just RUPI, kind of the standard one, and then put different substitutions, and then we're just wondering how are the states affected by different substituents. And then the question is kind of, first we look at the excited state electron delocalization. So it's the of course, you know, the unsubstituted system will have a delocalized state when you start out with, and then once it relaxes, a localized state. And then the question is, how is it affected by substituents? Is even the first state already localized? And then the other thing that we looked at is kind of substituent-induced electron localization. So the question is, an electron withdrawing group wants to have the electron in the excitation. An electron donating group will push the excited electron away from it. And so it also just played around with theater to quantify these effects. And so if you're interested in this, then you can check this new chemical science paper that came out. So I think it's just kind of a proof that you can really move these concepts also into a language that kind of is of interest to synthetic chemists. It's not just, you know, theorists playing around with pretty colors. But I think this can really move it into chemistry that way. All right, so that's it. And yeah, now I just want to switch the tone a little bit. So all of this was basically just kind of the same trick with this fragment decomposition. And then I just added a bit of kind of this charge transfer distance on top of that. But I just also want to discuss kind of some more a visualization technique that I'm kind of excited about. So here the idea is, you know, we look at oligothiophenene just kind of as any prototypical conjugated polymer. We do just some standard computations. TDFT can be through lip, doesn't really matter as long as you have a range separated functional. And then the question is, how do we analyze the states? So when you start out with, okay, you get the first 5 states, you get their energies, and then you see all these states are just combinations of different pairs of orbitals, and all these orbitals are delocalized pi and pi star orbitals. So then when you look at this list, all I can say is, okay, we have pi pi star states. But the question is, what does it really mean when we see all these combinations? And more specifically, for example, if we compare S2 and S3, the only difference is the minus sign here. If we compare S4 and S5, again, the only difference is the minus sign here. So clearly, just the shapes of the orbitals don't tell the whole story. But if you want to tell the whole story, then you need to take account of this sign. And the question is, how do we take care of that? And the good news is that we can do this kind of with techniques developed. So we can compute the CT numbers again to give us the conditional distribution of the electron hole in what is called an electron hole correlation plot. So this is for those 5 states discussed. Here we always, we plot the hole along the x-axis and the electron along the y-axis. And the shade gives us the probability. For example, here the highest probability is that the electron and hole are both on the 3rd or both on the 4th fragment. Here the highest probability is that the electron and hole are both on the 2nd or both on the 5th fragment. then if we go here, for example, this would be that the hole is on the second fragment and the electron on the fourth fragment. So this is a clear charge transfer configuration that plays a role here. Then here we have, again, more local. And here we have, again, more charge transfer configurations. And we also find nodal planes. So for example, we find a nodal plane here. We find a nodal plane here. Find two nodal planes here. And let's say kind of cross nodal planes here. So, and the thing that I kind of enjoy about this is then you can kind of go and think about how do solid state physicists think about excitons. And they think about, a hydrogen atom in a box. So kind of the electron and the hole are like the electron and the proton in a hydrogen atom. And then the whole thing is moving around in a box. So then when we look at the S1, kind of the S1 is the s orbital of the hydrogen atom and the ground state of the particle in the box. The S2 state is again the s orbital of the hydrogen atom, but now we have a nodal plane here because we have the particle in the box, kind of the sine curve. And then the S4 state has two nodal planes, so we have this double sine curve. And then kind of then when we go to S3, we see this is like the p orbital, where we have the nodal plane in a different direction. So we have a nodal plane along the electron-hole separation. And S5 is the combination. We have a nodal plane along the electron-hole separation and a nodal plane along kind of the joint quasi-particle. And so in a paper from 2016 with Steffi Mewes from the Drive group, so we did this for much more states, and you can very nicely kind of follow this pattern, how you get more and more nodal planes in the different directions. But then the question is, do we just want to look at these boxes all the time? And I mean, I've gotten used to it, but I don't know how intuitive it is to general public. So then what I thought about doing is, here again, we have our transition density matrix as a two-body function. And now what we're doing is we compute the square of the transition density and integrate it over one of those coordinates. But the trick is now, so you remember we did this before, and then we got the density of the excited electron. But now if we constrain the position of the hole to one fragment of our system, then we can get a conditional density. And then if we probe different fragments of our system, then we can see how does the electron density adjust conditionally upon whether the electron is where the electron is on the system. So yeah, Delia. So what I'm doing is doing this for the S1 state, for example. So it's that the S1 is here in the center, local on the center. The overall electron hole densities are delocalized. But now I can go ahead and put my hole on the right side of the molecule. And I see that the electron density is pulled over to the right. Then if the hole is here in the second molecule, I see the electron density relaxes a little bit. And if the hole is on this third fragment, then again the electron density moves over a little bit more. So this is how I can visualize this, and maybe kind of the way that's a bit easier to see. Again, these are the overall hole and electron densities. Now I say, okay, my hole can only be here. Then I see how the electron is pulled to the left. But now as I kind of scan through the system, I see how the hole follows the electron. And so this is just kind of the, let's say, large scale non-dynamic correlation between the electron and the hole as it moves through the system. That's represented by the multi-configurational character that I showed at the beginning. Okay, then, yeah, so then again, this is the same slide as I showed before. So here we also compute. Are you asking a question, Julio? Oh, okay. Then we asking, so then we compute the operator expectation values with analytic integration techniques. In this case, I'm not computing the linear electron hole separation, but root mean square electron hole separation, because the linear electron hole separation will always vanish in a centrosymmetric system, just as the dipole moment vanishes. But this thing is also well defined for centrosymmetric systems. And as I said, no fragment definition or population analysis, that's why I like these descriptors. So, and then for example, this is the same thing I showed before, and then we see the exciton size is 5.7 angstrom. So this is, I guess, maybe, so and the average separation is about maybe 1 ring or something like that, would be 5 angstrom, or 2 rings, and then we can compute the correlation coefficient. So in a sense, if you consider this as a distribution of data points, then you can compute the correlation coefficient. And here, this is reasonably well correlated. That kind of if the electron is further to the right, then the hole will also be further to the right. And if the electron is to the left, then the hole will also be further to the left. And for example, if I look at the next state, then I see the exciton size is reduced and the correlation is enhanced. So this is a more tightly bound state where the electron and the hole cling together more strongly and also move together through the systems more strongly. And you can also see this in the conditional densities. So our hole is either on the right, second, or third from the right, and the electron always stays on the right. So as you can see also in this plot, we have kind of an effective division into 2 parts here. So, and then, okay, just look at this again, for example, and this is the S2 state, and if we move this through the system, then we see the electron always stays on the left. And then as soon as we jump from the left side to the right side, then the electron also jumps with the hole. Because here we have this kind of correlation where the system is effectively divided into 2 parts, and either electron hole are always on the left or electron hole are always on the right. And then the third state, here, for example, the exciton size is large, and actually have a negative correlation coefficient. So they try to avoid each other dynamically, the electron and the hole. And maybe this is easier to see in this. So now the hole is to the left, the electron is to the right. Then as you move the hole, you see kind of the electron even has a little nodal plane here. And then if you move this through, then you see kind of the electron always kind of tries to be on the other side. So here we have an anti-correlation. All right, so that's all in terms of science I wanted to tell you today. Let's see what there is. So try to show you that we can assign the excited state character automatically. We talked about multi-chromophoric systems like DNA, push-pull systems, transition metal complexes. Then let's say kind of another logical thing is like Rydberg states versus valence states, where you can use these real space descriptors. N-pi-star versus pi-star doesn't really work with the tools we have now, because it's kind of a bit of a different philosophy, because you can't do the fragment-based way, but at some point this should be included. Then I showed the conditional electron hole densities, where we looked at excitons in conjugated polymers and how we can follow correlated motion. Then something else is, you can also revisit valence bond theory, and I think this is just something that I've been wondering about for a while. How do we understand ionic and covalent states in valence bond theory? So you can also, didn't include this in this talk, but I can show you the papers if you're interested. Okay, then if this interests you, then I would suggest 2 papers that came out this year. So then Introduction for More Practical Computation is in this JCP. This is a special issue in electronic structure software. So this is just kind of to get started with Theodore. And if you really want to dig into the theory and how do we kind of move from kind of pictures to actual understanding of the energies, then I would suggest getting this PCCP perspective that's also from 2020. All right, then the code that we have is, that on the one hand, this is kind of also what Antonio said at the beginning. On the one hand, there's Theodore. This is interface to different quantum chemistry programs. And if your favorite program is not on this list, let me know. I mean, usually writing these interfaces tends to be very quick. And then there's libwfa. That's integrated into different codes, and it's a bit more powerful because we can access more functionality by integrating it directly. So it's QChem and Molkas, and apparently also C4, but I've never used C4 myself. So, and yeah, I want to thank especially the groups that I used to work for. Then Patrick, my new PhD student here. And yeah, if you want to know where Loughborough is right here in the center of England, between Leicester and Nottingham. And yes, it's so many letters, but you just say Loughborough. Okay, thank you.
Thank you very much, Felix. It was very nice. The results and the way you, developed the theory and implementations in different codes. And it's really a powerful tool. And I think many of the people in the audience will start using it very soon.
Nice.
Now, I would like to ask if you have questions, please take this chance, because you are talking and listening to the author of the program and the analysis. So if you have questions, please ask it now.
Hi, Felix.
Yes, Sebastian.
Very cool, very nice talk. Thanks a lot.
Thank you.
There was quite a lot of stuff that I also didn't see so far, even though I saw the PCCP paper already. And just one question.
Yeah.
Towards the end, you showed these conditional densities.
Yeah.
And there you just missed a little chance, in my opinion, to just show all of them next to each other. If you can go to this slide.
Like, you mean like here?
Like here, exactly. So if you take the lower right part,
yeah.
If you take the lower right part here and plot all of the possibilities in a nice way, then you kind of again get this matrix on the top left, right, just in real space. And then if you make it in the right way, these two plots will really look more or less the same.
I mean, you're right. I guess you could make it a bit more pedagogical by kind of connecting. So every one of these plots is one row of this matrix. I'm kind of plotting the first 3 rows of this matrix. But you're right. I mean, I should play around a bit with LaTeX and kind of connect the arrows. And then let's say the second plot is equivalent to the first block by symmetry. So that's why I'm not showing the things that are equivalent by symmetry. But you're right, it would be more pedagogical to just put it all in, and I'll play around with that.
I could even imagine that this is also not only pedagogical, but also useful in another way. If you just try to mimic this matrix plot with real space things.
Yeah. I mean, I guess it's just, the matrix plots are a bit more compact than the real space things, but yeah, but sure, it's a good idea.
Cool. Thank you.
Antonio, if you have a question, you can open your microphone, please.
Hi, Professor Plasser. Thank you for the such great presentation. I want to ask you, how do you see the possibility of these new analysis tools that you showed that are so powerful to replace the usual canonical orbital, homo-lumo stuff that most chemists are used to do?
I guess it's kind of a hard question. I mean, I guess from a pragmatic point of view, it makes sense that, organic chemists synthesize their molecules and then they plot the HOMO and the LUMO, and as long as you kind of know the limitations. I mean, I don't think anyone will ever stop organic chemists from plotting homos and lumos, but it's just kind of, I think plotting a homo and lumos is an all right starting point. It's just kind of, you should know that there are tools to go beyond that.
Thank you.
Adelia, do you have any question? Adelia, your microphone is off.
Now it's okay, yes?
Yeah,
Yes.
No, I have no question. I got in the end, and I know this stuff of Felix. I'm working with him for a long time.
Yes, yes.
We changed several emails, several works. I know this. I love this work. He started to develop it when he was PhD in Vienna.
Yeah, exactly. Yeah.
And the Theodor is the name of his son.
The real Theodore is 6 years old already.
Yes,
So,
this is his name. Which is very nice. The meaning of the acronym of the Theodore is good question. But it was planned.
Felix, do you think you can translate this, I mean, the more negative or the more positive parts of the molecule in terms of electrophilic site and nucleophilic sites using your analysis?
I mean, I think kind of this one chemical science paper that's kind of from the Gonzalez group that we did, I think that kind of goes into this idea that you have like electron withdrawing groups and electron donating groups, and then you quantify the effects. So.
Okay.
So I think it goes in this way. Of course, I mean, we're analyzing individual excited states. So the problem is kind of if you want to assign some kind of effect to a group, then you have to average over the excited state. So that's why it's not completely direct, but you have to.
But in this case, I would say about only for instance, for the ground state, do the analysis in the single state, not involving excited states. Do you know what I mean?
I just hear. I think maybe Adelia's microphone is breaking the sound. Sorry. So thanks, yes. So what singular about and triplets? What do you?
No, you have the molecule in the ground state.
Yeah.
And can you do the analysis only for the ground state, for instance?
I mean, actually, Theodore, like this whole idea only works for excited states.
Okay.
So I think for ground, I mean what I would say is for ground states, there's also kind of this wide range of methods. And for example, there's kind of all this stuff by Martin Head Gordon with absolutely localized orbitals, and so I think for ground states there are loads and loads of existing methods. But I don't think, if you're just interested in ground states, then don't use Theodore, then use kind of the existing methods.
I'm asking you because I think most of the audience works with ground state only, so that's what I
mean, generally speaking, I think for ground states is a bit harder actually, because kind of in the excited state, you know, the electron is transferred from one part to the other part, and it's kind of clear what you want to look at. For ground states, you just kind of look at how bond critical points are moved by a little bit, and so on. So I think you need much more fine-grained tools for ground states actually.
Any other question? Danilo?
Yes, I have a question. In your example, the ground state is a closed shell system, okay? Right? And can Theodore be applied in an open shell system? for example, the absorption spectrum?
Yeah. So it's let's say there's no formal problem, and we have it implemented actually. Again,
because you have two set of orbital alpha and beta orbitals in the case of closed shell, right?
Yeah, but I mean, at the end of the day, kind of the charge transfer numbers at the end of the day are additive. So you kind of do the alpha and beta analysis separately, and then you add it up at the end. So let's say the equations work. We have it implemented in QChem, in Molcast, and Sebastian wrote an interface for Orca.
Because I'm thinking TDFT calculation, single reference. It's not a multi-configurational application.
Yeah, I mean like TDFT.
Yes.
So with Orca it works. So Orca, TDFT,
yes.
Orca and QChem. So with Orca and QChem you can do it. For the other ones that don't have the interface.
Okay. Thank you.
Yeah.
Hello, I do have a question. May I ask it?
Yes.
Yeah.
Professor Felix, thank you very much for the talk. It was very nice. I want to ask about this correlation between whole and particle. Do you have anything to say about how this is dependent on your choice of functional, or perhaps going to Kazashev wave function? How much the results might change?
Yeah, let's say the one elephant in the room is non-local exchange. So I mean, we also have a JPC lattice paper. So kind of, if you don't have non-local exchange, you don't have correlation at all. So for example, if you would do kind of the same pictures on a large system with PBE, then you just have the homolume transition. So you only get kind of this, let's say this Coulomb attraction between the electron and the hole derives from non-local exchange in the ground state. So this is actually also kind of a way to assess kind of the difference of density functionals and why kind of a local density functional will give you completely wrong results for these systems. That's your question.
Yes, thank you. And is it possible to be used for, say, Kazashev wave function? Did you ever try?
Yeah, so with Molcast and with Columbus, you can do it with Kazashev. I've done things. I mean, let's say kind of the theory of formalism as it stands now assumes that you have a closed shell ground state and single excitations. So as long as you have a closed shell ground state and single excitations, then you can use it for any method. It's just if you have a closed shell ground state and single excitation, then you may not be using Kazashev. But if you are, then you can use theater.
Yes, okay, I see. Thank you.
And I think people have used it for singlet fission, for example. And then I mean, yeah. So definitely we have used it with multi-reference methods with MRCI and so on.
So, any other question? So if you don't have any other, Sebastian?
Sebastian just said with Orca you can use an open shell ground state, and that's something Sebastian implemented a few months, half a year ago, I guess.
Okay. So if there is no other question, I thank you again, Felix, for the very nice seminar.
Yeah, thank you.
Professor, I see there are some questions on the chat bar. I would say for Sebastian and Max. No, sorry.
I think they were just kind of comments, right?
No question.
Yeah, sorry.
So thank you very much, Felix. It was really, really interesting. And I wish you keep working and getting more and more success as you have done in the recent years. Thank you very much.
Yeah, thanks, Antonio. It was nice to join.
Yeah.
Thanks. Bye.
Yeah. And I can tell you to the audience and to you also that the next one will be in November 13. And next week, I start to announce the next one, okay? So everybody will be invited again. Thank you very much for everybody, and I wish everybody a very good afternoon.